Hello Math 30-2 and welcome back. Today we're looking at mutually exclusive and non-mutually exclusive events. Mutually exclusive and non-mutually exclusive events really deal with or and and. When we're looking at it, we're adding them together, so it's mostly with the or, okay? But the and becomes very important as well. And if there is an and, that determines whether or not it is actually mutually exclusive or non-mutually exclusive. You'll discover that by doing these investigations here on the first 2 pages. And we're going to go over how to do, through other questions, on what is mutually exclusive, what isn't mutually exclusive, and how to solve some very interesting problems on that. So we'll have some time to go over that, and then come back to me as we'll start question number 1. So question number 1 is, in each case, state whether events A and B are mutually exclusive. So in our previous little, in your investigations, you discovered that mutually exclusive events cannot have an overlap. If you drew them in a Venn diagram, they cannot have an overlap. So it's 2 events where nothing is shared. That is mutually exclusive. Nothing can be shared. All right? Now, non-mutually exclusive mean there is an overlap. So if we added both things together, the things overlapped are counted twice. It would be, for instance, like grade 11 students and grade 12 students. Or it could be the high school basketball team and the high school basketball team and grade 12 students. Well, there are some high school basketball players that are in grade 12. You could look at it that way. Whereas if it's grade 11 and grade 12 students, they're completely separated. All right? So here's a first class example that we're going to look at. It says, in each case, state whether events A and B are mutually exclusive. Here is event A and B for number 1A. It says, a die is rolled. So we're looking at rolling a die. There's 6 sides to a die. We want to assume it's a 6-sided die. An even number occurs. And part B says an odd number occurs. Well, if we look at all my even numbers, they are 2, 4, and 6. And my odd numbers are 1, 3, and 5. Well, if I did a Venn diagram for that, here's my whole thing, there's nothing that could overlap. Therefore, these are mutually exclusive. There's no overlap there. Okay? Next one says, in an experiment, a card drawn from a standard deck of cards. So we have, event A says we want a face card. So we're looking at a face card, probability of getting a face card. Well, that's Jack, King, or Queen. Then it says a club is selected. Well, only in clubs we have an ace all the way to king. Well, isn't there a Jack, King, and Queen in clubs? So if I was to make a little Venn diagram for this, I would have my Jack, Kings, and Queens here, but some of those are also in the clubs, right? Some of them are clubs. So I have this or this. If I added them together, if I added all of these together, there'd be 12 here, and there'd be 13 here. But 3 of these are actually in there, so if you add those together, it's 25. But we counted the 3 in here twice. We have to take that away, and it's actually only going to be 22 different cards. If you were to set them all up and count them, there's only 22, because we have to subtract the overlap, the intersection. So it's not counted twice. So that kind of brings us back to earlier on when we were doing set theory in our first unit when we did the Venn diagrams. That really helps for this unit a lot. Let's take a look at example C. So 2 dice are thrown. So now we're looking at 2 dice. Okay? The dice both show the same value. So that would be, for instance, a 1 and a 1. Or we can say a 2 and 2, a 3 and 3, and so on and so on. The total score is 11. Well, if it's 2 dice, we can only have a 5 and a 6, or a 6 and a 5. So looking at that, can any of these be the same as those? No. They're all different outcomes, or all the events are different. Therefore, this Venn diagram will kind of look like this, and they are not related. There's no overlap, there's no intersection. Therefore, this is mutually exclusive. This one here, the first one before was not mutually exclusive because there's an overlap, so it's not mutually exclusive. Okay? So now we're going to look at example 2. Example 2 says, consider the experiment of drawing a card from a standard deck of cards. The following events are defined. So, event A, a face card is selected. Event B, a red card is selected. Event C, a club is selected. Event D, an ace is selected. And event E, a black card is selected. Now it says, which pairs of these events are mutually exclusive? Of these pairs, which are complementary? So complementary, if you remember way back, we even do this a lot in grade 11. Complementary means everything. So when we add them together, or that's everything possible in this set. Okay? So if we look at the high school, I always like looking at a high school. If I said all the boys or girls in the high school, we have the boys or girls. The boys are complementary of the girls because that makes up all the high school. But if I said all the grade 11s, and then the other one is all the grade 12s, those are still mutually exclusive like boys and girls, but in the high school there's also grade 10s. So they're not complements of each other. Okay? So here we go. So we're going to look at event A, a face card and a red card. Well, those aren't complementary because there are red face cards. Your King of Hearts is a face card and your King of Diamonds, those are face cards. Same with your Queen of Hearts, Queen of Diamonds. Alright, so a face card and a club. Those are also not mutually exclusive because there's an overlap in them. An ace and a face card. That is mutually exclusive. So I'm going to first write here, my pairs that are mutually exclusive is event A and event D. So there's one. The next one, so probability of A or D is mutually exclusive. The next one, a black card is selected. Well, half of your face cards are black, so that can't work. Now let's take a look at it. A red card is selected and a club. Well, those are mutually exclusive, so probability of event B or event, which one is it? A club, C. Those are mutually exclusive, so the probability of getting a red card or a club is mutually exclusive. There's no way you could have a red card that is a club. Let's take a look at the next one. A red card and an ace. Well, there are aces that are red card. That is not mutually exclusive because there are some aces that are red cards, so it is not mutually exclusive. And now we have a red card or a black card. That's mutually exclusive as well. So probability of B or E is mutually exclusive as well. Now, next one we're going to look at is club card. So a club and an ace. Well, there are aces that are club cards. A club card and a black card. Well, clubs are a subset of blacks. So, no, that one we cannot look at as well. Alright, so the last one is ace and black card. There are black aces, so that doesn't work. Okay, so which one of these pairs are complementary? So it has to be mutually exclusive in order for it to be complementary. So we're going to look at this, and I'm going to end up getting, for complementary, we have, which one fills the whole set? Well, the black and red cards, those are complementary. If I looked at A and D, so that is face cards and aces, well, there's still all those other number cards. So that is not complementary. There's still many other cards in the set. If I looked at this one, which one is this? Red cards and black cards. Oh, red cards and clubs. No, that is not complementary as well, because there's still spades, which aren't included between those. Now I look at the last one, red card or black card, those are complementary. So it's the probability of getting a red card or a black card that is complementary. Okay? This is the complementary one. That's it, because everything's either red or black. Okay. There we go. Let's take a look at this one here. It says, events have been represented in the Venn diagram. State the pairs of events which are mutually exclusive. So we're looking back to that Venn diagram from way back before. And we want the ones that are mutually exclusive. Just going to come in here a bit so we can see a bit better. So which ones here are mutually exclusive? Well, we take a look at A. Is A exclusive to B? Is there anything overlapping between A and B? No. So probability of A or B are mutually exclusive. What about A and C? Is there a mutually exclusive there? There's nothing in C that is in A. Therefore, they also are mutually exclusive. Okay, so these are A or C are mutually exclusive. The other one is probability of A or D. None of D is in A. These as well are mutually exclusive. Okay, so the union of A and D are mutually exclusive. There is no overlap. We won't have to subtract the ands. Now I'm going to look at B. B and C. Are those mutually exclusive? Well, we have this little bit here. That's an overlap. So some of C is in B and some of B is in C. Therefore, B and C are not mutually exclusive. Okay? Now we look at B and D. Well, none of B is in D. Some of B is in C, some of C is in D, but none of B is in D. So probability of B or D, the union of B and D, that is mutually exclusive as well. Next one we're going to look at is C. Well, C is not mutually exclusive to D, is it? Because we have this overlap here. There is some things that are shared. We'd have to subtract this and to find the union. Therefore, they are not mutually exclusive. Now we're going to look at question number 4. It says, use the given information and the probability formula to determine whether the events A, B are mutually exclusive. Well, the probability formula is given on your formula sheet. Basically, it's saying if it's mutually exclusive, A and B, if we add them together, there's no overlap, so nothing's counted twice. So if there is nothing intersecting, we could use the non-mutually exclusive formula, and if the AND is equal to 0, then it is going to be mutually exclusive, because there's no intersection, there's nothing overlapping that we have to subtract, so we're not counting twice. Now, we are going to look at this. I have the probability of A or B. Remember, or means add, or always means adding, is equal to the probability of A plus the probability of B. But we'd have to subtract probability of A and B, because that would be counted twice. If I looked at this, I had this and this overlap will be counted twice. If I had a number there, it's counted twice. Therefore, we'd have to subtract that. But if there's nothing there, that means there's nothing in the overlap, and that means they're mutually exclusive. They're exclusive from each other, so let's see if that works. So probability of A is 1 over 4. The probability of B is equal to 1 over 3. Probability of A or B is 7 out of 12. And then we want to see if this is actually equal to probability of A and B. We're seeing if that's equal to 0. If it's equal to 0, they're mutually exclusive. So I'm just going to go over here and add these together. It's equal to, now to add fractions, we need common denominators. Well, this is the same as 3 over 12. All I did was multiply the top here by 3 and the bottom by 3, and I multiply the top here by 4 and the bottom here by 4, and I'm going to get plus 4 over 12. Well, that's going to give me 7 over 12 is equal to 7 over 12. So we subtract the probability of A and B. Well, that's like saying subtract 0. So there is no overlap. We're subtracting nothing. So that means there's nothing of the events are overlapping. So this one is mutually exclusive. Good. Okay, I'll just zoom out so you can see that question. The next question says, A card is drawn from a standard deck of 52 cards. Use the formula to determine the probability that a 9 of diamonds or hearts is drawn. Okay, so we're looking at a 9 of diamonds or hearts. So, can there be any cards? Is a 9 of diamonds in the hearts? No, a 9 of diamonds is not in the hearts. Okay, so if we look at this, what is the probability of getting a 9 of diamonds? Well, that's 1 out of 52 cards. Now we know these are definitely mutually exclusive because there are no diamonds that are in hearts. There is a 9 in hearts, but this is a 9 of diamonds, which is very specific. So they have to be mutually exclusive. And the probability of getting a 9 of diamonds, there's only one 9 of diamonds in the deck, so that's 1 out of 52. Now the probability of getting a heart, well, that's a quarter of the deck. So that's the same thing as 1/4 or 13 out of 52. We add these together, and I'm going to get 14 out of 52 is my probability of getting this or a heart, a 9 of diamonds or a heart. Remember, it means adding. The next question says, a 9 or a heart is drawn. So this one's a little less specific. A 9 or a heart is drawn. Well, if I look at this, is there a 9 in hearts? Yes, there is. There are 4 9s. There are 4 9s. One of them is a heart. So we have an overlap here. If I was to draw my Venn diagram, there's an overlap here, and this little guy here is the 9 of hearts. He's in both. We have 3 other 9s here, and then we have 12 other cards there, right? And if we were to do that, 3 and 12 is 15 out of 52. But this is an easy one to find out. We're going to look at it using the formula and why we have to subtract. So, or 15, it's actually 16 out of 52 because the 9 of hearts. If we just added both of these, we would get 17 out of 52. But it's actually 16 out of 52 because we have this here plus this here. If you remember back from our Venn diagram parts and our subsets, so we go this, the 3 plus 1 plus 12. Okay? 3 plus 1 is 4 plus 12 is 16. If I just went 3, or if I went 4 plus 13, that's 17. So we have 1 too many. That's because of this overlap. That one will be counted twice. So let's go back to this. It says, a 9 of hearts is drawn. So I'm going to take this out. So we want, and we know this is not mutually exclusive. I'm going to put a 9 union hearts here. I'm going to put an N for 9, which is equal to the probability of getting a 9 and plus the probability of getting a heart. Now we have to subtract this little bit there, probability of getting a 9 and a heart. Okay, we have to subtract that overlap of the and. Otherwise, it's counted twice. So the probability of getting 9, there are 4 9s out of 52 cards. Okay, what is the probability of getting a heart? There are 13 out of 52 hearts. Now, what is the probability of getting a 9 and a heart? Well, there's only one of those. That's 1 out of 52. So we start adding this together. We're going to get 13 minus 1 is 16 out of 52. And that can be simplified. Okay? Both of these can be divided by 4. So it's going to give me 4 out of 13. All right? And there we go. And that is the probability of getting a 9 or a heart. Is 4 out of 13 simplified. Last question. Or sorry, second last question. So we have blocks of different shapes and colors are to be placed in a bag. All right? There are 3 cubes. There are 3 colored cubes here. So in our cubes, I'm just going to straighten this out a bit better so you can see it clearer. So, there are 3 colored cubes, 1 blue, 1 red, and 1 green. There are 2 pyramids, 1 red and 1 yellow. There are 5 cylinders, 1 blue, 1 yellow, and 3 red. So altogether, how many shapes do we have? 1, 2, 3. Well, we have 3, 2, and 5, which gives me 10 shapes. So there are a total of 10 shapes. I just want to know that, okay? Now I'm going to say how many red are there. There's 1, 2, 5 red. I'm just putting on the side here everything we know. How many green are there? There are 1 green. Okay. How many blue are there? There's 1, 2 blue. And how many yellow are there? There are 2 yellow. Right, that's just to organize some of my information. And then we have this part here, 3 cubes, 2 pyramids, 5 cylinders. So now I have everything slightly organized. It can make me go through the question a bit better. So it says, determine the probability that a block selected at random will be a pyramid or a cube. Well, there is no overlap between pyramids and cubes. You're either a pyramid or a cube. No overlapping, so these are mutually exclusive. Now we look at this. How many pyramids are there? Now I'm just going to probability pyramid or cube, or is always the union sign, or cube, is equal to, I'm just going to put a square like this for cube because the cylinder starts with the C as well, is equal to the probability of a pyramid plus the probability of a cube. And we don't have to subtract anything because they're mutually exclusive. There are no pyramids that are cubes because we're not looking at colors. So we look at this. The probability of cubes is 3 out of 10. And the probability of pyramid is 2 out of 10. Which gives me 5 out of 10, which is the same as 1 out of 2. All right? Next one says, will not be red. So it will not be red. Well, there are 5 red, so the probability of it being red is equal to 5. Okay, so the probability of it not being red, well, oops, 5 out of 10, which is 1 out of 2, because there are 5 red. So the probability of it not being red is 5 out of 10, which is the same as 1 out of 2. Because it's everything else that's not red, well, there's 5 other colors. We have 1 green, 2 blue, and 2 yellow, which is 5. Okay, so that's the probability of it not being red. Remember, this donation here means not. So it's not in that set of red. So, will be red or a cylinder. So if I look at this, there are some that are red and a cylinder, aren't there? If some are red and a cylinder, that means we have an overlap. If I drew this out, red and cylinder, this is red, this is a cylinder, we have that overlap there. Some of them are both. So we're going to have to subtract this once, okay? Because otherwise, we're counting them twice. So these are not mutually exclusive, whereas this was mutually exclusive. Take a look, we have probability of red or cylinder is equal to, or is the same thing as union, probability of red plus the probability of a cylinder minus the probability of red and a cylinder. Okay? We continue this. And what is the probability of red? Well, there's 5 out of 10 blocks that are red. What is the probability of cylinders? Well, that's the same thing. That's 5 out of 10. Now, how many of those are red and a cylinder? 3 out of the 10, because there's 3 red and cylinders, so it's 3 out of 10. Now we look at this, that gives me 10 out of 10 minus 3 out of 10, which gives me 7 out of 10. And that's how we get that. So these are my 3 answers. Okay? Last question. Tom and Andrew were asked to solve the following problem. 200 people with neurology symptoms, which include headaches, backaches, participated in a study to evaluate the pain relief medicine. All the people took the medicine, and the results were as follows. 60 people experienced headache relief, 126 people experienced backache relief, and 36 people experienced relief from both. Notice how it says relief from both? This is going to be the and one. This is back and head. So this is P, back, and head. Okay, so that's the back and head is that one. So what is the probability that a person takes the drug, experience relief from at least one of the two symptoms? So if we're using the probability of at least one of the two symptoms, that is this or this. So at least one. So it's this or this. Okay? But it could also be and that. Alright? So, what is the probability of a backache? Well, that is the same as out of 126 people, we have 126 all over 200. The other one is, what is the probability of both? Well, that's the same thing as 100 and, sorry, where are we here? 36 out of 200. Alright? Now, if I looked at this Venn diagram, it says at least one. So it's this or that. And we would also include this overlap if we add them. The subtraction, just make sure we don't count them twice. So how many had at least two of the symptoms? So that's going to be probability of H or the back problem. So we really have to look at what the question's asking here, what it means. It's not saying which one has this or this. It's saying a person who takes the drug experiences relief from at least one symptom. Now, for this one, I'm going to get 0.3, or 60, out of 200, plus 126 out of 200, plus, notice how these did not say only? These here did not say only. If they said only, I'd have to add all three of these together. But they did not say only, so I have to take away this so it's not counted twice. And then we have minus, not plus, we subtract 36 out of 100, or out of 200. Now if I continue this, what's going to give me 186 minus 36 is going to give me 156 out of 200. Okay? And if you use your calculator, you could cancel that down. Now part 2 says neither of the symptoms, so nothing was helped. So that is the probability of not having a headache or backache being helped. So that's the not. So that's the exact opposite, which is equal to 1 minus the probability of headache or backache in this case, because it's everything else out of here. So it's all of this we want. Everything besides that shaded area. Well, that's going to give me 1 subtract 156 out of 200, which is going to give me the same thing as 44 out of 200, which is the same thing as 11 out of 50. Okay? So I'm assuming this one here then is, if that's 11 out of 50, this is going to be 39 out of 50 if it's simplified. Okay? Now, Andrew decided to solve the problem using a Venn diagram, complete the Venn diagram to solve the problem. So the Venn diagram, he first had 36 here. So then, how many people have a headache is actually 1, or not 60, minus 26, or minus 36. So how many people with experience of back relief is 126 minus 36. So really, we subtract 36 twice. So what do we end up doing? This is the same thing as we add all of these together. We're going to get 60 minus 36 plus 36 plus 126, and then we have to minus 36 because we have to subtract that overlap because out of this 126, 36 are in there. Okay? Now when we get that, we end up getting a total of, notice how these cancel off? So it's pretty much 60 plus 126 minus 36, which is the same thing as what we did there. And that's going to give me a total of 156. And then it's out of a total of 200, so it's 156 out of 200. And then for the second one, he wanted everything else, so you just go 1 minus that, okay? So that means if I have 156, there is a total of how many people? Of 244 on the outside, because there's 200 altogether. All right, so you could do this with the Venn diagram if you find it easier as well. So good luck, and I'll see you tomorrow as you tackle on the assignments, and good luck.